Thank you.
Okay, thank you, Laurie and Bengt, for the invitation to speak here. It's always a pleasure to talk to an audience that's a majority, what I call emerging scholars or students. I want to share with you my story about chemistry and its service, I hope, to humanity. I hope you will agree with me by the end of my talk. But there has been a lot of questions, I think, of these wonderful speakers that we've had about what interested them in chemistry or what interested them in science and what was the perhaps the spark point. And I want to just head off those questions and just give you the answer now. As far as I'm concerned, in regard to that question, I went into science because I saw things like this when I was 10 years old. And I was captivated. I had no idea what they were. I've never seen them before. I opened a book and there they were. And I just fell in love. And my story is really that you could potentially make remarkable things from very unremarkable beginnings or unremarkable start. And I think that that's what you have to keep in mind when you're choosing your discipline of study. You have to see what is pulling you towards it, or where are you getting pulled to. And the second point is that when I did undergraduate organic chemistry, and all of you will do this, probably you've already done it, you crystallize organic compounds. This is probably benzoic acid. You crystallize it by adding ether to a solution of it, and it comes down like snowflakes. Okay, and I saw that, and I was like, I think I'm going to be a chemist. I'm not going to listen to my parents who wanted me to be a doctor or engineer, but not chemist. And so I persisted, and I didn't really listen. And then as I was choosing graduate school, again, I went with beauty, okay, and the love of molecules. And so I chose, in those days we didn't have internet, we had booklets that we basically leaf through the booklet about what professors are doing, and we apply to those universities where we want to work with those professors. And this is something I saw, and I thought, wow, this is so amazing. I'd love to know more. I'd love to work on this. And so I went to meet the professor, and I said, if this professor is a nice guy, I will join. And so he interviewed well, actually, and I joined. But he was a tough mentor, which I needed to learn rigorous science, and it was a really great experience. But my first project, when I was a graduate student, was to take a proton out of this V10O28. This is completely useless stuff. I mean, it's not very useful. The only useful thing about it is that it was a nice research project because there was a lot of nice colors. But I was supposed to take one proton out of that. So it's a deprotonation reaction, one of the simplest reactions that anybody can do. Well, it took me a whole year to actually get to the point where I may have done it, okay? And as I was walking across from one building to building to analyze what I had made using vanadium NMR, I was taking this solution, this nice orange solution, and I was, by the time I reached the NMR, my solution has changed into something like this, okay? It became brown gunk, basically. And so I went back to the lab and I was depressed. I turned around to ask a senior postdoc in the group. I said, what do I do with this? And he said, oh, Omar, it looks awful. Throw it away. I was not going to throw away a whole year of work, okay? And so what I did is I set up a crystallization. And Yeah, there. And what I made was quite unique. It was this ball-shaped compound. It's like a rice ball. And it was a trap for any molecule that has a nitrile in it, okay, like benzonitrile or acetonitrile. The nitrile part stuck in the center of the pore and was selective to nitriles. And this ball was the very first inorganic host-guest complex, was the very first soluble molecule that can trap molecules within it. So, and there's been nothing like it since, actually. This is a unique, and started a whole new area of vanidates. So, I was raised as a chemist, as a molecular chemist, learning about molecules. We've heard a lot of great talks yesterday, especially yesterday, about how we design molecules, the role of molecules, and chemists have been, over the last, I would say almost 100 years, have honed in their skills on designing these molecules with great precision. Okay, of course, you can make pharmaceuticals and things that are very useful that way. But they're molecules, they're discrete. Okay, so then we heard from Professor Jean-Marie Lane about what happens when you start bringing molecules together and they start interacting through, in his case, through hydrogen bonding or through weak interactions. And you saw what he can do with that. So what I really was interested in is what happens when I start stitching molecules together by strong bonds. What happens when I shove them closer together and connect them by strong bonds? What kind of things can I make? And I hope they would be beautiful, first and foremost. But really, at the fundamental level, I wanted to understand, how do I build large structures or materials or extended structures by stitching molecules together in a potentially by design or in a rational way? So that's the question that I set out to do or to answer when I became an assistant professor with an independent group. So my journey up to this point had nothing to do with being highly intellectual in my choice of a problem. It was just the love of doing research, the love of how beautiful molecules are. And I think that very often your interest arises from things like this. You don't have to be necessarily a well-planned interest, okay? So, but now I had to become serious because I was tenure track and I need to do something that would be useful. And so I thought, well, people make extended structures by what we used to call shake and bake approach. They mix stuff together, they heat them up to high temperature and they get their material. Well, that wasn't satisfactory to me because I wanted to use organic structures that wouldn't survive at high temperature. So how do I take building units that involve organic molecules, which we can functionalize potentially in future and make designable materials? So the problem is that we faced is that as you stitch molecules by strong bonds to make these extended structures, you make things that are not crystalline, okay? And in my mind, I needed crystals so that I can wake up every day and enjoy research, but also because we can characterize crystals on the atomic and molecular level so that I know that I made that material, but also I can then modify it and still be able to characterize it. So what in the end worked was linking a transition metal ion with a charged organic linker like this. And to make an extended, this is infinite, it's a layer, and between the layers, a pyridine, part of the reaction conditions, sticks between the layers, and we were able to take the pyridine out and put it back in and things like that. But again, this was the very first time that somebody could crystallize a metal organic linked by these strong bond. So, but we wanted to develop this further, and we wanted to understand the conditions under which these compounds crystallize. So we look in the literature, and every inorganic chemist, every chemist should know that the metal acetates, the copper acetates and zinc acetates have this structure. They're molecules, and the core of these molecules is basically you have a dimer of metal, either copper or zinc, that is bridged, and you learned about chelation, I'm sure, bridged by a carboxylate. So by 4 carboxylates, you can see that it's bridged by 4 carboxylates. So our idea was that instead of acetate, if I can have a diacetate, then I could extend this structure infinitely. And what could those materials be like, and what properties would they have? Now, the key to crystallizing anything is to make sure that your building units can attach themselves and then break away while they're being crystallized, so that they can fix any mistakes. If they approach in the wrong geometry, they can detach and come back and fix. It's like asking you to go out in the field and make a big circle. That doesn't happen instantly. There's a lot of holding hands and correction to make that circle. It takes time. So you have to control the kinetics of your reaction. If the kinetics is too fast, then you make too many mistakes that there's no time to correct. If it's too slow, then you don't grow the material to the level that you want. And so these are the conditions. What we did is to take the acid, this diacid, dicarboxylate, very common material called terephthalic acid, and a solution of zinc nitrate, very simple reaction. Under these conditions, you can crystallize an extended structure. Well, how does it work? What made it work is, of course, a student that I met when I was a student on an internship in China. And when I became assistant professor, he wrote me a letter, a handwritten letter that said, "Professor, I see that you, Omar, I see that you're a professor at ASU, and I see that you're making these extended structures. I think I can do a better job than you." And so I said, "Well, that's fine. If you can do better than I can, please come." And so he came and he did this. And I think it was absolutely brilliant, is that to slow down, basically this reaction, these two will not react unless the base deprotonates this acid. And to slow down this deprotonation reaction, he diluted the base in toluene. Okay? So he did a classic crystallization. Here is a solution of zinc nitrate and the acid in DMF, and now you've got your base in toluene that diffuses in slowly to make a crystal. Okay, very simple reaction, very simple strategy to make sure it was successful. And what did we make? We made this structure, which is exactly what I described before, the cluster that I described before, linked infinitely to make a two-dimensional grid. And because terephthalate is a long linker, and this cluster is large, now you have space into which those solvent molecules that were present during the reaction are trapped. Okay, and so then later we showed that in fact you could remove these DMF molecules and the structure still stands. Okay, and I'll show that shortly. Well, all right, if you can do one reaction, you can do the other. Turns out that DEF, diethylformamide, when you heat it, it produces very small amounts of triethylamine. That triethylamine can deprotonate the acid slowly, and you can make this kind of cluster or a crystal. This crystal is a primitive cubic made from tetrazinc units. Again, the dicopper acetate that I described, and the molecular version of this tetrazinc cluster called basic zinc acid have been known since Bragg time in 1930s, and where he was studying them with X-ray crystallography. So they've been known for a long time in chemistry. but no one has either thought about linking them together or succeeded because of the crystallinity challenge. But here you have now a three-dimensional structure. It's not layered, but it extends in 3 dimensions. And this is what it would look like. We use the yellow ball to indicate the space within which you could trap things. And this is the isotherm. This isotherm shows that nitrogen can go into the pores and out of the pores in open circles in the same way. So that means that in the absence of any stuffing in the pore, the structure remains open. This was truly powerful because up until this point, all porous materials like zeolites were inorganic. Or they were porous carbon, but porous carbon is not crystalline, and you can't really functionalize it because it's made of carbon. There's no CH bonds. But here, we had plenty of CH bonds, and we could use not just this dicarboxylate, but we could use even longer dicarboxylates or functionalize this unit, this phenylene unit, to make functionalized pores. The surface area for this material was 2,900 meters squared per gram. That's a number that you derive from this nitrogen isotherm. 2,900 meters squared per gram is 3 times the most porous carbon in those days, or 6 times the most porous zeolite. Okay, this was for a young assistant professor, this was terrifying because you're actually breaking a 1,000-year record of porosity. And so we made sure that we verified this result by sending it to independent company to measure it. But they were getting 2,900, but sometimes they were getting 3,300. And I gave a talk at the German zeolite conference. They invited me to give a talk about this when this paper came out in '99. And the big professors in the front didn't believe any of this, but there was somebody in the audience. His name is Ulrich Müller. And Ulrich later revealed that he thought that that number, the surface area, was so unbelievably high that he thought it had to be a misprint. Okay, and he's at BASF, he was at BASF trying to reproduce our work. And he was telling me about it, that they can, in fact, get something even more than 3,300 meters squared per gram. That was a start of a very beautiful relationship with BASF, a start of a collaboration where BASF showed that, in fact, you can scale up MOFs to multi-ton quantities. Okay, we were making them at the milligram scale in the lab, and everybody was saying, well, these are boutique materials, meaning that you can't make very much of them. But they showed through our collaboration that, and now they're scaling up, at least a dozen MOFs on multi-ton scale, and I'll show one of them shortly. So that's how this chemistry started. And now we can play with it, because now we know how to put things together, how to stitch them through strong bonds. And now we can change the size of the linker, the length of the linker, the functionality that we might put on the linker, and the connectivity, not just ditopic. What we can do tritopic, we can do tetratopic, and all the way to 12-topic. So we can also not just use zinc, but we almost could use any metal in the periodic table. Okay, almost any metal in the periodic table. We can change the size of the unit, the metal type, and also the connectivity. We can make many different forms other than this primitive cubic. And above all, in so doing, you're functionalizing the pores, you're changing the size and geometry, and you're precisely designing materials now in 3 dimensions. So it opened up a big field. I call it an infinite open frontier. More than 10 to the 100 structures are possible. It's almost infinite. And already there are almost 100 research groups in almost 100 countries working on these materials and on their applications in clean energy, water, and biotechnology, and even medicine. So reticular chemistry then, we defined it in 2003 as the chemistry of linking molecular building blocks by strong bonds to make crystalline extended structures. There are three components in this definition that are very important. Building blocks, okay? Now, as a chemist, I can take very large units, I can take inorganic units and organic units and stitch them together by strong bonds. And I want to say something about the strong bonds because I want to make materials that are going to trap CO2 from flue gas so that it doesn't reach the atmosphere or even take CO2 out of the atmosphere. I want to do this. I want the same material to be used over and over again for years so that we don't create more waste. And we want them to be, of course, crystalline. I said the virtue of that. So the result has been metal organic frameworks, or MOFs. But also we can do it without metals. We can stitch just organic compounds together by covalent bonds to make COFs. Okay, and notice I always have a vowel in the name so that it becomes a word. Instead of saying MOF, you can now call it a MOF or a COF. And more recently, just further in terms of the power of this chemistry is that you can even make woven structures, molecular weaving, where a thread, an organic thread, interlaces with another thread to make a three-dimensional structure that's not just porous, but also flexible. I won't talk about that today, but I want to focus more on the other two classes. So the strong bond building block approach has been quite fruitful, and it came from interest in just designing beautiful structures. I didn't really set out as an assistant professor to solve anybody's problem. I was just interested in making beautiful structures and trying to answer an intellectual question, which was, how do I design structures in the way I just described? So why do they have such a high surface area? Okay, the need to know. Several of the previous great speakers mentioned that, the need to know. And now you take a crystal of this MOF 5, the one with the yellow ball, and you stick it in a capillary and you put it on an X-ray diffractometer. Okay, this crystal has been completely evacuated from all the stuffing that is in the pores, and now you're just looking at the framework. Okay, it didn't break apart. Usually crystals will lose their monocrystallinity when you take away the solvent that is contained within them, but here it didn't. So this is the crystal structure. We actually can see the crystal structure without any stuffing. And now to figure out why does it have a high surface area, we have to figure out where these gas molecules were residing in the structure, because wherever they sit, that represents the surface area onto which I can trap gases, and that's related to the surface area. So you see here, when I introduce argon, okay, it sticks to this site, to the metal site, which are the corners. If I introduce nitrogen, it does exactly the same. This is nitrogen electron density from the X-ray X-ray single crystal diffraction. But it's not just the metal unit that's acting as an adsorptive site, but also the organic units, okay? The faces and the edges. So almost, let's say, everything you're looking at in a MOF is an adsorptive site. That's why they have this extraordinary high surface area. I like to always try to think and view things from a different angle, and I think that's part, and again, another speaker mentioned that. You know, you take a cube that has a surface area of 1 meter square per gram, let's say a grain of sand, and I can expose every atom in that grain of sand to make a high surface area material. So really, every atom in the substance becomes a surface. That's really the moral of the story of MOFs, is that by making a scaffolding, you're making a structure where every atom potentially, almost every atom in the structure is an adsorptive site. That's why they have extremely high surface area. This is a surface area that we can achieve right now. So the material is right here. So you've got your metal oxide units in pink, and they are linked. Now notice that now I've used a trigonal linker that has many exposed faces and edges. And notice that this is a porous material, but the pores have no walls. It's a scaffolding. And that's designed so that to expose maximally the atoms in the structure. And that's why they have extremely high surface area. And I always like to say that a gram of this material, which is no bigger than a coin, has a surface area of an entire football field. Okay, that's basically the footage onto which you can store gases. So you can imagine that this has been quite exciting for solving the climate problem, other problems. Climate problem, we know what's causing it. It's a gas, CO2 gas. So this is ideally suited to be at least a platform onto which we can bind CO2. Okay, the previous speaker, Catherine, did a great job at telling us the harmful effects of CO2, so I won't talk about it, but it's melting the Arctic ice. But it's also CO2 and global warming is making our weather patterns more severe. You see here in this illustration, this is a study of 153 events of land heat waves, and most of them, the great majority of them, have been more severe than usual or than the average. The same thing goes for ocean heat waves and wildfires and everything listed there. So climate change, we are now more aware than when we first started MOF chemistry, that CO2 is a problem, and thankfully society appreciates that, and governments throughout the world are investing money into solving the problem. And a lot of this money, we could have it. The chemists can have it, because we are the ones that could provide that solution. This is Malibu burned in 2018. About a quarter of Malibu burned, and this is how many acres burned in California in 2022. And water is another problem. This is the Hoover Dam in 1983. This is in 2003, and this is in 2022. When I was a professor at ASU, it was in between 2002 and 2003. But recently I went there, and it was really low. So this is a problem. Water is a problem. And this reservoir supplies almost 20 million people with water. Okay, so let's talk about carbon capture, and I want to talk about carbon capture from air. That's a more difficult problem than from flue gas. So if my material works in air to take CO2 from air, because where it's at about 400 ppm, it will work even much better if I put it in a power plant to prevent CO2 from going into the air. So this is the experiment that you have to do. This is ultimately the experiment that has to be done, where you take air, you put it through your material, and you look at what happens on the other side, if indeed it's trapping CO2 or not. So the minimum requirements for a carbon capture material is that you have to have a high capacity. It has to be selective, because you have to pluck out CO2 from the air, from other gases. Your material has to be water stable. It has to be oxidatively stable. It has to be cyclable. Like I said, you have to cycle for years. It has to have low regeneration temperature. Once you bind it, you have to take it out. And you don't want to put in too much energy to remove it. And the solution has to be scalable. You have to make this in multi-ton quantities. And unfortunately, we have a lot of materials that we can look at, but we don't have a lot of candidates. All these materials have problems meeting even the most lowest requirements, which is capacity, regeneration, temperature, and cyclability. And I'll show you that MOFs are okay for flue gas, but not for air. But coughs might be or are really good for capturing CO2 from air. So here's how this chemistry works. Here's a MOF, and we call it MOF 808. Let me see if I can play this. Yeah. MOF 808 is made from zinc oxide units that are linked by trimesic acid, and you see these glycemic units, the NH2 units, sticking into the pores, and the pores are replete with these. And these NH2 units attract CO2 from air. They basically, without them, you can't bind CO2 from air. Okay, so we study what is CO2 doing into the pores using solid-state NMR. And what it's doing is when it's humid, you make bicarbonate, and you make also carbamic acid. But when you don't have a humidity, when there is no water, you make carbamate. Okay, so with water, you're shifting the equilibrium to carbamic acid and bicarbonate, and luckily, that's better than when it's dry. When it's dry, you need 2 amines for each CO2, so you need double the amount of material. When it's wet, you only need 1 amine per CO2. So we are very fortunate to find that this is the case. Okay, so how does it work? How does it work in real under air? So air is, as I said, is 400 ppm CO2, and now I expose my MOF, the MOF I just showed you, to a wave of air containing 400 ppm of CO2, and this is the result. You see, immediately, CO2 is taken up by the material. It drops down to 0. Okay, so it takes CO2 out of the air. Of course, it takes up a little bit of water as well. You need it. And it stays in the pores. It stays in the pores, and then when all the amines are saturated, CO2 comes out. Okay? So this means that I can separate CO2 from air with 1.2 millimole per gram capacity, which is really above what is required if this material can cycle 100,000 cycles. Well, it turns out that in this experiment, this material cannot cycle more than 500 cycles because although it's stable in water and acid, but it's not stable in base. But coughs can. We worked very hard on making very stable coughs for the last, since 2005. And the latest is that you can make a cough out of carbon-carbon bonds and carbon-nitrogen bonds, some of the strongest bonds in chemistry. And you can make crystalline structures of this kind. Okay, and I just have here the powder diffraction to show the crystallinity, but also the stability in 12 molar HCl. Very strong acid, saturated KOH, even corrosive media like N-butyllithium. This is the kind of stability you need to have a material that's going to be in a power plant for a long time. So I just want to show the result. This is CO2 from open air in Berkeley. Okay, this is the CO2 in the air in Berkeley during this experiment. This is the humidity. It goes up and down over a 20-day period. And this is the uptake. Okay, so as the humidity goes up or down, your CO2 uptake also scales with that variation, but you're taking up over 1 millimole per gram consistently, and the material is stable. If you look at just the humidity, let's say at 37% relative humidity, you'll see that the performance is exactly the same between day 1 and day 20. So I think that we have a material that can separate CO2 from air, and the same material takes up double the amount when you do it in flue gas, of power plants. Now already a colleague of mine at University of Calgary has made a MOF that has 2 to 4 millimole CO2 capacity, and it's already since 2000 or up to 2021 had cycled over 450,000 cycles. This has already been commercialized, and as you see, it doesn't work in air, but it works in CO2 flue gas. and that has high CO2 content, like for cement. So this has already been deployed, commercialized in cement plants, and this is the material that BASF is already, they have announced that they are scaling up that MOF to several hundred tons per year, and it's being deployed in several cement plants in Canada. Okay, so the next thing that I want to discuss is water. Okay, this is a picture of water crisis up to 2040. They expect it in 2040, and you can see parts of the world that we think are humidified are going to be stressed because we're using too much of the underground water. So the idea is that if I could make a material that traps water from arid air or desert air, that material would work even in the humidified region where you might have water, but the water may not be clean. So we're not at a risk of drying up the air because there's a lot of water in the air. There's almost as much water in the air as we have in lakes and rivers on our planet. And in fact, if we were to give each person on our planet 50 liters a day of water, we would have only used less than 1% of the water in the air. There's plenty of water in the air. Okay, the reason it's challenging to take water out of desert air is because there isn't much of it in the air. If you look at this, if I'm in a city where the temperature is 30 degrees C and the relative humidity is 20%, to take water out of that air, I have to cool down the air to 4 degrees. Okay, that's very energy intensive. However, if I have a MOF that plucks water out of the air, concentrates it in its pores, now I can, let's say, and put it in a box, close that box, expose it to the sunlight, where water heats, the sunlight heats up the box, water comes out of the MOF and condenses. So basically, because the MOF can concentrate water into the pore, I can increase the humidity inside that box to 90%. I can take desert air and make it tropical air. And to get water out of tropical air doesn't take much. You have to only reduce it by 4 degrees in this case to get the water out. And so I am looking at the time, so I'm gonna skip the introductory here and just go down to one of the great materials that we made. We call it MOF 303. Again, it was characterized by single crystal X-ray. We know exactly where all these atoms are. It's made from aluminum oxide rods that are linked by perazolase. These are organic units called perazolase. The green is nitrogen. Those are part of the organic linker. So what I want to show you now is a movie where we have to show you where each water molecule is binding. But before that, I want to just say that if you're a water molecule moving through the pores and looking around, you're looking at a grid of hydrophilic and hydrophobic pockets, okay? Hydrophilic, hydrophobic, hydrophilic throughout each one of these pores. And what happens, the first water molecules from air, of course, go to the hydrophilic sites, and when those are saturated, it bridges over the hydrophobic sites through water-hydrogen bonding. And that's what you're going to see here. I'm going to take one pore out, cut it longitudinally so that you can see what's happening inside. Then you'll see water binding to the hydrophilic sites, okay? And now start bridging over the hydrophobic sites because of course, water is hydrogen bonded in the pores. And to take it out, you either expose it to ambient sunlight, where the MOF is heated and the water comes out, or you could do it electrically, as we did here in this device. Okay, this is a device, this is electrified, this is plugged into the electric, water goes in through that door, goes into the MOF is heated, and you saw a bit of condensation there, but in the end, it's collected at the bottom, and now you can collect pure, ultra pure water, okay? And this device it is as large as a small microwave oven, and it only has 200 grams of MOF. And it gives you 5 liters a day, and the MOF is graded to be in the device for the lifetime of the electronics, so 5-6 years. So the student on their own volunteered to drink this water. Okay, this is supposed to have sound, but the sound didn't work. He's supposed to say, "Oh, it's delicious." Okay. Eugene is living, and he's the CTO of a startup that's commercializing this. But we tested the water, of course, and there's absolutely no metal, no organics. It's a very pure, it's actually the most pure water that you can get. Okay, that water, of course, is distilled. It's just pure water. So to really drink it, you need to mineralize it. You need to put some minerals in there. Otherwise, it will not taste really that good. It will be a little bit bitter. Okay, but we work on many prototypes and we test, but this is one that I call rain in the box. Okay, and I know in Lund, this probably will not impress you because we have a lot of rain, but parts of the world where I come from, this would be really something. Okay, but here's a material, and it works in the same way as the electrified device, but here we're trying to deliver even more water, and now you can see actually rain and the water collected. Okay, so it works, the MOF works. And the students even went to Death Valley to show that, in fact, this MOF works under the harshest of conditions. So the MOF here is put in pancake configuration, and during the night they open the device, water from air goes into the MOF. During the day they close it, and when they close it, it heats up from the sunlight. There is no electricity here, just ambient sunlight, and you can collect water. Should have seen a bubble there, but believe me, it works. So based on those results, you can get water either without electricity, without power, other than the sunlight, ambient sunlight. And this is if I have 1 ton of MOF, this is the amount of water that I'll be getting per day. And if it was plugged in, this is how much water I'm going to be getting per day. So that's what those startups are now working on. The latest is one that is delivering, this is as large as a small refrigerator, and it's delivering 22 liters per day at less than 400 watt-hour. Okay, that's about 3 cents in California. In Texas, it's cheaper, it'll be 1 cent. Probably in Sweden, electricity is maybe double what it is in California. But we're talking about first-generation devices that are already giving us water very cheaply. If you add only 2 carbon atoms to that linker, you can increase the uptake of water by 50%. And you can take out, because they're hydrophobic, you can take out the water at even lower temperature. Okay, so I have 2 minutes, and I want to cover what we are doing with AI. So it took us 25 years to get here. In the case of MOFs, 30 years to get here, to go from molecule to material to engineering it into a device and then system, and it's very close to getting to society. My colleague in Canada already has a material that's in a cement plant. So can we use AI to speed up this? There's no reason why we couldn't speed it up. And so we are working on a different cycle we call digital innovation cycle, or the digital discovery cycle, where now you could use robotics and image recognition that uses machine learning and build big data, do machine learning on this data, and to give you conditions under which you can discover the next generation material. And we're working on this. This is our Gen AI project. I can't talk too much about it yet because we are still well, we're almost at the draft stage, so I can tell you about this later. But here, all I can say is that by following this cycle, we are able to make materials that are not obvious, that were not obvious to me. Okay, and if I'm an expert in the field, so if it's not obvious to me, then it's doing something new. But in the meantime, we've been experimenting with ChatGPT, where we can use just simple conversational language to train ChatGPT to text mine, image mine, be a supervisor, do molecular editing, and even be a research group. All, by the way, at this point, supervised by human, or a collaboration with a human. And here we took, okay, I'll be done in 30 seconds. I am 15 seconds over time. So we took 250 papers that describe the synthesis of MOFs, and we trained it to extract 10 parameters in the synthesis. Okay, the starting material, the solvent, temperature, you know, the usual things. And it did it in less than 2 weeks, and this was the most primitive. This was our first use of ChatGPT. I mean, it would take a researcher months to get there. I think the reason I like this is that it puts all the facts in front of the researcher. Now, a researcher can make decisions based on all the facts rather than just chemical intuition, which is not always right, not always based on facts. So it does that with 95% accuracy. The research group is what I really like, okay? And here I showed you that by adding 2 carbon atoms, you can increase the water uptake by 50%, and you can use ChatGPT to give you different possibilities. But somebody has to crystallize this, and without what I'm talking about, it would take a student a year, maybe 2 years to crystallize this. Even the most brilliant of them takes a long time because they're searching in a small reaction space. But with ChatGPT, we're able to take a material from, here's experiment number 9, where the material is not crystalline. Here's experiment 84, fully crystalline. Okay, that's done in less than 2 weeks. Okay, so there is something there, right? It's so now I have sort of switched almost 50% of my group to do AI, ChatGPT. We can optimize the uptake. We can get the theoretical porosity and okay. We can also train it to go through the literature and ask questions, intelligent questions that require multi-stop, that require logic, and actually will also provide not just the questions but the answers. Okay, so we can discuss that in the question-answer session. So I just want to conclude by saying we've developed atomic molecular precision in extended, infinite 2D and 3D, where I hope helping to solve the climate problem. And I think AI for reticular chemistry is just the first step in getting emerging scholars such as yourself to plug into research, and also other emerging scholars around the world to have to lower the bar for entering into research. Okay, so I want to acknowledge my wonderful students, the funding agencies, and thank you very much for your attention.